Thank you very much. Can you hear me? Well, we've been sort of looking at clouds now for more than 20 years. But the philosophy has been to do it step by step each time, take one additional effect and see what one can learn from it before we put more parameters into it. If you have a large number of parameters, some of which you're not certain about, then of course you're not quite sure exactly what your computations are saying. So that was the thinking. So what I want to do is this. Some of the people here will have heard me speak about some of our earlier work on clouds. But still, in order to see where we are, it might be good to see what that earlier work said. Because some of the major conclusions came from that earlier work, and I want to tell you what they are before I go into what we are doing. So, in the first place, clouds are really, in my mind, the grand challenge problem in atmospheric sciences today. Whether you're talking about climate change, or you're talking about the monsoons, clouds are the weakest point. And that International Panel on Climate Change has said that many, many times. This appeared as an appeal to physicists to start looking at clouds again. For a long time, there have been efforts to model these clouds. And a brief summary from a fluid dynamical point of view appeared in Turner's very well-known book, Buoyancy Effects in Fluids. Turner himself tried some clever experiments. He realized, of course, that buoyancy is an important factor. And well, he made tabletop experiments with bubbles released and so on. But none of them really looked like a cloud. Here, for example, is one where he had that bubble kind of experiment. And you see, it's growing linearly, just like a standard plume. Standard plume, conventional plume, grows linearly with height. And you see the experimental points, they line up exactly where a classical plume does. And at that time, well, big computer solutions were still not very common. And the attempt was made to describe it in terms of similarity theory. Self-similarity or self-preservation, as some turbulence people like to call it. Where the basic assumption is that the mean flow, as well as the Reynolds stresses, scale the same way, with the same length and velocity scales. Well, that didn't get very far, and I'll show you why. And Turner concluded that at present there is an alternative model. There are lots of cloud types, but the ones that we are most interested in is cumulus. That's what really runs a great deal of things in the tropics. The cumulus is a real flow cloud. It's a fluid dynamicist cloud, so to speak. Some of those other clouds, flow is not so terribly important. So it seemed to be the right one to try and tackle. And started by trying to see how shapes like this, for example, two typical clouds. You can see how crinkly this is, fluffy balls. But this is like a tower. Both of them are cumulus shapes. What goes on? What is the fluid dynamics which determines why is this or why is that? And is there anything that we can understand about the structure of those clouds? One major problem is entrainment. How much of the dry air gets into the cloud? And the first choice for making those assumptions, we will go back again to Turner, was to say, from a hypothesis made by Taylor, that the entrainment velocity into the plume or into the cloud is proportional to the mean velocity characteristic of the cloud flow or the mean flow or the plume flow. So you take the centerline velocity and you take this as proportional to that. Often works well in the problems that Turner handled, but it doesn't work well in clouds at all. And in fact, in the 1990s, which is just about the time when we were starting our work, Emmanuel said that old similarity plume model is thoroughly discredited. It really didn't tell us much about clouds. But clouds can be very different, shallow, deep, fluffy, smooth, boiling, louders, chaotic, ordered, etc. They're all flow clouds, and that's what makes them most interesting. So here are the first three models that were tried. None of them gave anything looking like a cloud. And we started looking at what heating does to a plume. Heating is the proxy for the release of latent heat when a phase change occurs. And the main difference was we said, well, heat release is only over a certain region. What happens to the flow? And a cloud is not a steady cloud. In fact, if you look at cloud lifetimes, they're actually not very long. Median of 10 minutes if you look at the old movies. For some of them can be much longer lives. They may have a much longer lives. So really, the kind of flow that we set up was what I call a transient diabetic plume. And the first thing that we found was that if you wanted to put it in one of those pigeonholes which fluid dynamicists have, about where this flow fits in, I would say a cloud flow would fit in the transient diabetic model. And I want to show you why. This is the overall picture we have of what we are doing in terms of the cloud. It's, of course, a cloud is a very complex flow, coupled system, microphysics, thermodynamics, droplets, particles, and so on, phase transitions, heat release, and then the cloud fluid macro dynamics, I'd like to call it, what you can handle at the Navier-Stokes Boussinesq level, which of course affects all of these too. So it's a closed cycle. But I'm only going to look at this green rectangle here, by and large. This is where we are doing it. Because at that time it seemed to me that that's where we seem to understand the least. So here are the equations. They're more or less the standard equations for the Boussinesq approximation. As we know, the density changes are taken to be so small that the fluid is really incompressible, can be treated as incompressible as far as continuity is concerned. But when you come to momentum balance, the change in density doesn't affect the inertia terms, but it does affect the buoyancy term. So it is converted, the density change is converted to temperature through the coefficient of expansion. G is the acceleration due to gravity. G is so high compared to these accelerations that a small temperature differential is enough to make this term large. And then here is the energy equation. This is the temperature differential, incidentally. A standard plus a term due to the amount of heat you're putting in. And that can be a function of x and t. Here is the vorticity equation. Now, I write down the vorticity equation even now, because what happens to the vorticity is very interesting and sometimes very unexpected. And I think, therefore, that understanding the vorticity field might contribute to our understanding of what happens in the cloud. We make a non-dimensional parameter for the amount of heat which we are putting in. If the total amount, that's the total amount of heat which you are putting into the flow, acceleration due to gravity, coefficient of expansion, densities, specific heat. B is a length scale, U is a velocity scale. Best when you are looking at clouds and the cloud base, and Q is the total amount of heat you put in. You can also make a local heat release number. So that's our model. There's a plume which starts from a hot spot on the ground. This is a classical plume. Condensation, heat release, that becomes a cloud. Now, I tried to do this with steam and air and so on for 6 months as an experiment. It didn't work out very well. So it turned out that it would work best in water, although it looks so funny to make clouds in water. So really, we made an experimental apparatus which looks like this. It's about a 1 meter square box, about 1.5 meters high. And you can think of this as the flow, equivalent of the ground. We make a plume here. There's a plume chamber. A hot bit of fluid oozes out into this tank of water. We have a cage here of electrodes. The plume fluid coming in is electrically conducting. You add some acid or something. The rest of it is electrically non-conducting. It's deionized water. So this is really a conductor inside an insulator. And by applying voltages across these grids, you can put in heat, ohmic loss, and you can control that. We have done it in such a way now that if you wanted to repeat a heating history, you can push a button and you can get that same history again and again. It's a transient flow, so you may want to repeat it again and again if you want averages. And you can also make some stratification at the top and bottom. Otherwise, this is neutrally stable. Well, you can make that scale analysis from the heat release in the cloud fluid of the order of 1 watt per cubic meter. And it turns out that if you do it in water of that size, it's a very manageable 1 kilowatt. If you put in about a 1 kilowatt heat into water, into a fistful of water, you're reproducing the condition of the cloud. So we set it up. That's a standard starting plume, the kind that Turner studied, for example. This is the same starter plume, but with heat released here. And you can see it already begins to look different. You must forget the part below this. That part of the cloud which you never see in the atmosphere becomes visible only after condensation. So, in fact, you can produce several different kinds of cumulus clouds, at least 3. And I want to compare quickly real clouds. Here are the pictures, and the ones which you made in the lab. See how many we could reproduce, what kind we could reproduce. This is a congestus, so it's pretty dense, as you can see. Several kinds of congestus clouds. Here is a mediocris. Well, a mediocris is really not releasing any heat, no condensation taking place. It is, as the name suggests, a sort of dying cloud. It's not a very active cloud. You can make that by playing around with the amount of heating you're doing. Is that another one? And here's the fractals. As you can see, it's as if somebody is really pulling it out into pieces. And you can make that as well. Another fractals, things hanging down. But this needs some stratification at the top. In other words, what I'm trying to say is that what we learned from those pictures is that you can make cloud-like flows in the lab without too much difficulty, with just a few control variables on heating and some stratification. Nothing else is required. But very importantly, the non-dimensional heat release number must be the same as of the cloud. The Reynolds number is not the same, but the heat release number must be the same. If you get the heat release number right, then with these 4 things that are mentioned here, we can get a wide variety of cumulus shapes and clouds. So what happens if you start making measurements from them? We're divided by the diffusion term. Okay, now with see the diffusion here, the Reynolds numbers are pretty low, 2000. So the diffusion is small but not negligible. Certainly not realistic. The Reynolds number here is not realistic. Incidentally, one of the things that this is showing is that the Reynolds number is not as important as you think. There are certain problems for which the Reynolds number is important. For example, mixing. And even there, I personally feel you don't have to do this at very large Reynolds numbers. I think a great deal can be learned by doing it at smaller Reynolds numbers, provided we are beyond what is called the mixing transition. But I'll come to that later on. Well, this is, we first started steady flows. And you can see what happens immediately. That's the diameter of the plume, steady plume, versus the height. We heat inject here. This line is what the conventional flow does without the heating. But as you start putting in the heating, these values of the heat release number, you can see that the width actually shrinks. In fact, it seems to sort of become constant. So in other words, the cloud doesn't grow like a regular jet of plume. It actually is more and more coming towards one of those towers which you saw in those slides earlier. That shrinks. The mean velocity at the center line increases. That's a reciprocal of the center line velocity. So that's what it would be in a regular jet. But if you heat, this comes down, so the velocity actually goes up. So it accelerates, as you might expect. Even the turbulence intensities also go up in absolute value. That scaling there, that doesn't vary with x. So you can actually have turbulence intensity go up. So that tells you why, if you have a bumpy ride in the aircraft and you're crossing a cloud, that's what happens. And here is the entrainment coefficient. You can actually measure the mass flux and compute the entrainment coefficient, which is the way that these free turbulent shear flows have been looked at. M is the mass flux, the rate of increase of mass flux. P is the diameter of the flow, center line velocity. And you see, as you go up, that is the heat injection zone. The behavior in most of these is roughly like this. It starts out, takes a little while, and then reaches a peak, and then comes down. Of course, that doesn't happen in this particular flow. And this particular flow, I think, was somewhat different from the one we had. This was an experiment made in the United States with the same apparatus. It also shows this big increase and a decrease, but it goes negative and is rising again. Partly, I think, because their heating was very much higher. It had a Richardson number of 40, which is a very large one. But incidentally, it also shows that there is no universal curve, and quite a bit of it may depend on how much heat you put in, how you put it in, what its distribution is, and so on. So there are a variety of other parameters also. So what is happening to the flow to cut down the entrainment, as you saw it there, as you move out? Incidentally, that picture shows that the self-similarity model doesn't work. If it were working, your alpha E should have been constant. Clearly, it doesn't work. Why doesn't it work? Well, you take a cross section. This is taken with basically with PIV and so on. You take a cross section of that flow of the plume, then there's no heating. It look like this. That's dye concentration, basically. I do a wavelet analysis on this, a 2D wavelet analysis. And at some wavelet scales, well, out of that, what seems like a mess, this pretty ordered structure pops up. In other words, this mess in the flow is actually hiding at a certain scale a relatively well-organized toroidal vorticity structure. And we know that from other measurements that something like that is there. And this is part of the coherent structure. The flow, the turbulent flow, shear flows are not as disordered as was thought. There are coherent structures there. But if you add heat, that's what happens to the flow. You can see how qualitatively different it is, dramatically different. And that old structure has disappeared here. And here is part of the flow which is unmixed. Incidentally, like the protected core that meteorologists talk about, these clouds, there are cores which actually don't mix. They have much of the mixing occurs outside. The same phenomenon is repeated here. And we can, in fact, therefore, see what is happening there. It's really quite something. I'll not go into this, it will take me too much time. It's just a comparison with certain other kind of calculations, shows the measurements and the calculations. So we come to the conclusion that it's a good hypothesis to make a cumulus cloud flow a special example of a transient diabetic plume. So all these things are important. So we now made a DNS of a cloud in a box, simplest thing. Temporal simulation. Let's see. And that's the box. The fluid expands this way, the jet of the plume, and we put in heat in time. This, in the laboratory setup, we put in space, we put in time here. And the jet expands this way. And you have to solve the same equations. I'll not go into how we solve it. But yeah, that's what I want to show you. This is the unheated flow. And there is that coherent structure. You can see. This is that toroidal vortex structure that we talked about, conical. Now you put heat into it. That's what happens. You can see that this is incidentally the vorticity, the azimuthal component of the vorticity. You can see that the difference is dramatic. It is huge. The vorticity field goes up enormously. And in fact, if you want to find out how much, you can compare this with the usual jet. where it starts off, falls there in the first few diameters as the jet starts. Its transition to turbulent flow reaches this peak and then slowly decays. But you put heat in, this is what happens. This is Enstrophy now on a logarithmic scale on the ordinate. And you can see how extraordinarily the Enstrophy increases. It's an order of magnitude. It's more than a factor of 10. So you had a vorticity of 1 declining the ordinary jet. You now have something like 10 times that, increasing still with the distance at the end of that flow. The vorticity, therefore, is dramatically increased. In fact, to exaggerate things a little bit, the vorticity which you see in a cloud, what they suggest, really comes from the heating. The fact that it started as a plume is almost irrelevant because of the Baroclinic torque. I had an equation for the vorticity there where there was a term. I think it will probably come back. The term which shows the Baroclinic torque. Now, this is our third generation TNS code. We tried to compute an actual transient diabetic plume. Various numbers here, very much the same as before. So first of all, visually, what do you get? You have what we computed here. You have what you may observe here. These are the parameters. As I told you, the Reynolds number is not very high. It does matter for mixing, but in other cases, it doesn't seem to matter a great deal. So you can see that the flows are very similar. And it comes from the Baroclinic torque. Many of the things can be understood from the Baroclinic torque. If you look at what's happening across this flow, the temperature is highest in the middle. So the buoyancy force is largest in the middle. And as you go towards the edges, it's smaller. So there is a Baroclinic torque operating here, this way on this side, this way on the other side. That Baroclinic torque increases the velocity in the center line and diminishes it at the edges. And that's really what accelerates the flow. And it has a variety of consequences. But there's not only a mean Baroclinic torque, there's an instantaneous Baroclinic torque. And this is a 3D view. If you split the flow, let's say it's cylindrical, one of those tower clouds, that's the Baroclinic torque which drives up the flow. But there are also fluctuating Baroclinic torques operating here this way, involving the temperature gradients, of course, radially, and the velocity components across. And that enormous increase in vorticity, how did that happen? Especially in last, actually, I think I forgot to point out one thing. I didn't have a spectrum there. The interesting thing is that the high frequency vorticity has a much larger increase than the lower frequency vorticity. I see that I must have skipped that figure. But anyway, if I take a balance of what is happening to the Enstrophy, that starts with the Navier-Stokes equations. Plain, no heating. That's the mean vorticity for a steady flow. And these are the various terms which contribute to the mean vorticity. This is a turbulent transport of turbulent vorticity. This is a vorticity production term, mean vorticity times S, mean stretching rate. Turbulent flow stretching, turbulent vorticity here, and viscous diffusion. Now, if you write an equation for the turbulent Enstrophy, there are a large number of terms actually. There's a generation by the mean vorticity gradient here, capital omega. A turbulent transport, third order term, one derivative. Stretching by mean strain, stretching by turbulent strain, a viscous diffusion term, and the viscous dissipation term. Well, I don't think I have, let's see. Okay. We have a few minutes. So I won't go through a detailed order of magnitude analysis of this equation. It's interesting. The only terms which survive that order of magnitude analysis are these two. Stretching by turbulent strain and viscous dissipation. Now, that is for the regular jet. But if you now do it with heating, to cut a long story short, this is the equation for the entropy. It contains three terms. One from the fluctuating vorticity itself, another dissipation due to the fluctuating vorticity, there should be primes here, and a third one, the source, the Baroclinic law. Now, the point I wanted to make here, one thing to remember is that, I'll continue for a few minutes. One thing you have to remember here is that if you have a flow with a certain vorticity, you do something to it, and you change the vorticity, as you're doing with heating, or even without heating, the vorticity does not scale the same way as the velocity does. As in self-preserving solutions, it should do. Compared to large-scale vorticity, let's say the turbulent shear flow, vorticity increases like the square root of the Reynolds number. Becomes very large by itself. If in addition you have heating in, it becomes absolutely huge. That's really what we see. This term, therefore, plays a leading role in the dynamics. And here, well, that's the continuation of the. So you can see that here. This is the vorticity surfaces in a regular plume, and vorticity surfaces in a cloud-like plume. You can see how much it has changed. And you can also see the change in the spectrum visually, because small-scale motions actually just crowd the whole flow. Here is the mass flow. If you take the mass flow as we normally do in a lab experiment on turbulent shear flow, you would integrate it across the flow. That is the outer curve here, the black curve. But this is DNS, so you can actually go to the edge of the flow, vorticity, find what the actual increase in the mass of the turbulent flow is. So that's always a little less. It does depend a little bit on the threshold you use, especially in this part. But by and large, there's a part of the flow which is not turbulent in this black lines. So this is one more reason why I now feel that the old, what do you call it, entrainment coefficient, Taylor's definition, I don't think it's really relevant to cloud flow problem. It doesn't remain constant. Depends on what is happening. And in any case, what really matters is the turbulent flow which gets in. And that's not the same to the total mass flow. So here is the velocity scales and so on. That's the way here. In this transient flow, you have a variation in height of the same alpha e. You can see large fluctuations. It goes up as it did in the earlier case, comes down, and really becomes very small. Well, I think that I just want to show something like a movie. Let's see. This is one of the DNS solutions for the transient diabetic plume. These are vorticity contours inside. That's the scale. So reddish is very high, and blue is relatively low. That's the way it goes. And you see, the vorticity is actually out there at the top, and in the middle here, just above the heat injection zone. Huge, and again a factor of 10 there, till it begins to look like a cloud. And I have a similar movie for diametral cross sections. This is the last slide. How does entrainment occur? There's now a big debate going on about how entrainment occurs. Every now and then, it looks as if in fluid dynamics, every now and then you have a big debate on entrainment. And new proposals being made. This is one standard picture. What happens? Fluid coming in like that, parallel flow, of course, convoluted edge, fractal edge for the jet, fluid goes in. But what happens is more like this. It's not at all parallel. A lot of fluid coming in from outside, rushing in only at certain places with very high values. There's only a finite lifetime. These pictures show that entrainment is really episodic. It's not continuous. It's not that flow is coming in from outside. In fact, the outside flow is also organized, which people have missed. It's quite organized flow. Depends on the vortices inside, the coherent vortices inside. This is actually that same vortex ring you saw. That vortex ring, this part of the vortex ring, is driving the flow in. Well, that's another big, let me conclude. So, latent heat release is what's very important to the dynamics. The transient diabetic plume is a good textbook fluid dynamical model of what happens in cloud flow. Wide variations in the entrainment coefficient. Baroclinic torque drives the flow engine. And vorticity is very important. And that's a description of the last result. Thank you very much. I'm sorry, I exceeded my time.
What if you include the radiative cooling on top of that plume, like in a real cloud?
That vessel usually. Oh, you mean in the
real
flow?
Cumulus Cloud, there's a radiative cooling on top.
Yes, that's always been on our mind, but we haven't had time to do it. Okay. Because each one of these suggests something else. But I think there are ways of doing it. At least one idea we toyed with was that you had, let's say, very thin coils which carry some very cold fluid. And you get it from the cold storage. You can cool it if you want.
I'm asking what will happen if you include that?
Okay. Now that will, of course, change the density field. And if it's cold, it gets heavy. Therefore, the fluid will spread out. You know, it will actually become more or less like laminar flow. You might have seen clouds in the evenings, for example. They rise, they spread out if there is an inversion. The temperature is increasing, for example, or if there is stratification. And oh yeah, that's right. This assumes that the atmosphere is at rest. Okay. Just to make the problem simple. Yes, of course, the mean flow will affect.